go faster. So we're going to continue our discussion today by talking about nonlinear sigma model. I'll briefly review the previous lecture. So last time we talked about critical exponents and statistical field theory. Imagine you have a spin system, you have some external field, and this is your you add this term to the to your Hamiltonian sourced. So Helmholtz free energy is -1/beta log of the partition function, and you can find magnetization by taking derivatives with respect to of the Helmholtz free energy respect to B and setting it external field and setting it equal to 0. Then there was the Gibbs free energy, which is Legendre transform of this that resembles effective action. We talked about phase transitions. Phase transitions are non-analyticity, non-analytic behavior of free energy as a function of thermodynamic variables. Of course, it can really only exist in some form of thermodynamic limit. Is it clear what thermodynamic limit is meant here? Okay. There is a critical temperature when there are phase transitions, and when you have first order phase transitions, you have discontinuity in the first derivative. There's latent heat. Continuous phase transitions are when the first derivative is continuous, but higher derivatives are not. And these are characterized by universal critical exponents, and they're described by conformal field theory. For instance, when you have the critical Ising model, if your degree of freedom is some S, the connected two-point function will decay like this near the criticality, near the critical temperature. This is called correlation length. Correlation length goes to infinity. Now, the behavior of the two-point function at criticality will show some shifted two-point function, some shifted exponents. These are critical exponents that you could read. There are some forms of anomalous dimensions. In near criticality, you can have your correlation length could show some exponents that are universal. You see universality in specific heat, or the magnetic susceptibility. Magnetic susceptibility is the zero frequency limit of the two-point function. Now, imagine you see such a phenomenon in some critical system, and the question is, what is the CFT that describes this theory? Well, if you do see some critical exponents that are not zero, like for example, the two-point function does not scale like free theory, then you should have an interacting theory. So you should have an interacting fixed point in the infrared that calculates these critical exponents. Now, we saw that in D larger than or larger equal to 4 dimensions, there we couldn't find any interacting fixed points based on only Z2 symmetry. So scalar field theory. For D less than 4, we saw that there could exist fixed points, and the idea behind this was the Wilson-Fisher fixed point. Other examples, important example, is the 3D Ising model. Okay, questions? So we talked about the ON model. This is when you start with some sort of Lagrangian density like this. There's an ON symmetry. The field is this vector. And we're expanding around phi equals 0, right? This is what the answer is. This is what the Lagrangian around phi equals 0 is. This is an expansion around the trivial fixed point, this theory. And in the IR, there will be spontaneous symmetry breaking. So there will be an interacting fixed point with broken symmetry, which means that the value of this vector field, the one-point function of the vector field, will be non-zero, non-vanishing. It would be some one-point function like this. Now, we saw that every time you have every time you have spontaneous symmetry breaking and you have a one-point function, it's a natural thing to do to calculate, to construct the effective action or the Gibbs free energy. In the thermodynamic analogy, what is the effective action at one loop? It's just the action corrected with quantum quantum corrections at one loop and quantum corrections at one loop are captured by I over 2 logarithm of the determinant of the kinetic operator expanded around the spontaneous symmetry breaking point. In the case of ON, we saw that there's a mass matrix. There is a mode that is I think in our convention we picked the field to look like this. There was some sigma field. This is the direction where it's broken, and then there are pi i's. Right, there's a pi I here. Sigma field and pi I ended up with different masses. That's why you have a mass matrix. We calculate the renormalized effective action. This is what it looked like. Near Gaussian fixed point, MR squared and lambda R are small, right? Yeah.
Yeah, sorry, just when you say, okay, the effective action of one loop is that.
Yeah.
At n loops. Because I remember that in the homework we have to calculate these kinds of things. And the other says, okay, if you integrate all the Fermi field or the Fermis, then you have only one loop. But then it says find the correction to higher loops. How would you?
So you need to give me a little bit more context.
So like this is why is this called a one loop correction?
Because we calculated using one loop. This is just a one loop expansion. You don't recall the derivation?
Right in this example, I think the one loop fraction comes from the log term, the log term.
Log term, yes, log determinant.
And in our homework, we are asked to calculate something similar, but for a Fermion version. And in the question, it says we only have to just pass integrate out the Fermion field, and we can get the one loop question.
Yeah.
But the question is how can we get the higher?
So that's a very special theory, I imagine. I don't recall what the example was. But in a general theory, calculating the higher loop is a pain. It's just very, very difficult. That would mean that you would have to solve the quantum field series of higher orders, arbitrarily higher orders. That's a very simple theory. And one way to actually think about how it works is that you have to look at how we derive this formula, right? What is that? So the derivation of this formula comes from the following fact. So we had some path integral over some degrees of freedom. Let me call it, well, pi a. Right? So what did we do? We expanded this around some phi 0 of a. Expanded this in terms of these fields that are sigma and pi I, right? Pi I. Now, what does it look like? Let me schematically write what it looks like. It looks like, can you see here?
Yeah.
It looks like d of, now your new variables are like this, right? There will be e2 minus s of phi naught of a that comes out, right? And now here you're going to have some expressions like this. Good. So what is H bar? H bar sits here, or if it could be couplet. These are the couplets, right? So let's just look at what this guy is. S of sigma of pi k is a kinetic operator sigma sigma plus pi plus higher order, right? So what we did was in this, so of course the interactions, this is the kinetic piece. If you just ignore all the higher order terms and just look at the kinetic piece, this answer is a Gaussian integral, because these are Gaussian. You could do, and the result is ln of determinant of this operator, inverse. Right? But that's just one loop. Now, to higher loops, higher order contractions will come in. That's just a messy calculation to do. Now, if you happen to be working with a theory where it's so simple that you could perform the path integral like explicitly, then you have a full answer that you expand order by order. Sometimes you might not be able to perform it like to all orders, but there's some sort of nice structure. So it depends on your example. But in general, one loop is pretty universal and nice, but above that is just detail, depends significantly and they're crucial in the details of the interactions. Any other questions? All right. So yeah, this is the effective action. Around the Gaussian fixed point, these two variables are small because we treat both mass as other like other couplings. So this is just a relevant coupling, and this is the marginal coupling. So what we did was once we calculate the one loop effective action, we'll look at the Callan-Semanzik equation for the effective action. The Callan-Semanzik equation for effective action takes, well, we could explicitly expand this in powers of lambda and m squared around the fixed point, and we found that the beta functions for the coupling are lambda squared over 8 pi squared n plus 8, and then the gamma of m, which is the running of mass term, is like this. So this is in 2 plus 1 dimensions. And the answer was pretty disappointing, right? So the beta functions are positive for all values of n, which means that it actually gets worse as you go to larger n. And that's just bad. The theory doesn't exist in the infrared. Well, the theory is free in the infrared, if you wish. And it has UV problems. Good. But let's just be a little bit more specific about this analysis. So what is the beta function? M dm of lambda is beta of lambda, right? So m, take it to be b lambda. B is that dimensionless parameter that tells you about what scale you're working with compared to the UV scale. So this is b del b of lambda, and you could integrate from both sides this way. What you obtain is that the integral of the coupling over b lambda from lambda naught to lambda is minus log of 1 over b. This tells you that the beta function grows in the IR. When beta is if beta is negative, then as you go towards the IR, the coupling will grow. So beta expanded in the following way: beta squared, lambda squared, beta 2 lambda squared, beta 3 lambda cube plus blah blah blah, right? Why do I not include a lambda term? Why do I start at or the lambda squared? Why can't there be a lambda term? From which equation?
So second line,
No, this is just general analysis. This one?
Yeah.
Yeah, but beta of lambda is an undetermined function. It could be anything. The thing is, so what are you doing? There's physics in this. You have a theory that's a CFD. It's a conformal fixed point. It has lambda equals 0. It's a trivial fixed point. You're perturbing around this, right? So whatever beta functions are, lambda equals 0, they should be 0, right? What happens, now this is a fixed point. The fact that it's a fixed point, it tells you that it has to be stationary. It cannot have an order lambda term. Because if it did have an order lambda term, it would just run. It would not be a fixed point. Fixed point means that it has to be like this, right? Now, this is a crude analysis. If your theory has many, many couplings, this is not a 1D, it's a higher dimensional thing. So you're working with, there could be saddle points, there could be all sorts of things, right? There could be maxima, minima. It's tricky, complicated. But the first derivative, and at least in one direction, is 0. Here, it's a simple setup where just to isolate a single coupling, lambda, and this starts at order lambda squared. Okay, very good. So just plug this inside this equation, and you find that if you integrate this, just pick the lambda squared term. If you pick the lambda squared term, you could do this integral explicitly minus 1 over lambda at scale b plus 1 over lambda. Lambda is the UV value of the coupling, is minus b beta 2 ln of 1 over b. Now it's pretty clear that if beta 2 is positive, as we found for the ON model, the coupling will decay in the infrared. The theory is free in the infrared. If beta is negative, now the coupling can grow. You might end up with a fixed point in the IR. Good. All right. So in this particular case, when it's beta, so here's I'm gonna make a very important point. So I'm just looking at the beta squared term, beta 2 term, lambda squared term, right? That correction comes from one loop. That's a one loop correction. If you integrate this equation, so this is, I'm plugging in, you could think of it as this equation is it's the integrated version of beta function running of couplings where you only know the beta function up to one loop, right? So you could invert this and you find lambda at some lower scale in terms of the UV value, right? Once again, it's the same phenomenon that as, because what happens is that when b is less than 1, right? So this guy is a positive number. So if beta 2 is positive in the infrared, the coupling will go away. If beta 2 is negative, it can grow in the infrared. Now imagine if this beta 2 term is 0, so what you end up with, a coupling that remains marginal at the one loop level. You have to go to higher loops to determine the fate of this operator. It's possible that it remains an exact quantum marginal deformation. In that case, you don't have a CFD, you have a line of fixed points. You don't have a fixed point, you have a fixed line. You have a theory and a deformation that if you change for any value of coupling, you have a different CFD. There are examples of such theories, unequal force shipping angles as well. Okay, if beta is negative, the coupling can grow in the infrared. That's good. We're going to end up hopefully with an interacting theory, sensible theory. When beta is positive, there is a little bit of a problem. Not only that the theory in the infrared is going to be trivial, but the UV theory is sick. Why? Because you could easily invert this and view it as this is the observed value at some low energy, and this is the UV lambda. Now, it's pretty clear that for some value, UV value, the coupling will blow up. So what have I done? I'm taking the one loop answer literally. And I see some scale at here. If I run further down, the coupling is going to go down. Beta 2 is positive. Now, what if I run up? What you find is that it doesn't grow. It does grow, but it blows up at some finite scale. This is called the Landau pole. So, for example, so at some finite value, the coupling goes to infinity. So this is clearly, there are many issues here. First, you're plugging in one loop value. As you start growing, integrating up, you need higher order terms. You can't trust that. But yeah, this is called Landau pole. But the theory is also in the UV. The fate of it is unclear. All right. QED has a Landau pole, by the way. So let's go through this. Lambda phi 4 and d equal 4, beta function was 3 lambda squared over 16 pi squared. This is positive. There's no interacting infrared theory. QED and d equal 4, if you write the beta in terms of E, electric charge is E cubed, but the coupling of the theory is not the electric charge, it's electric charge squared over 4 pi. Do think about why. Why is the coupling E squared over 4 pi and not E? It should be straightforward. But anyway. So when you write it in terms of alpha parameter of QED, beta of alpha is 2 alpha squared over 3 pi. This is positive. Here we also have a Landau pole. It's a famous QED Landau pole. In the ON model in D equal 4, similar problem. So far we've had we found no interacting theories in 4 dimensions. QCD will be the very first example. Well, non-abelian gauge series will be the first examples that we'll get to in the next part of this course. But today, what we're going to do is we're going to continue in line of building theories in lower than 4 dimensions that are that exist. So we went through the Wilson-Fisher. I'm going to review Wilson-Fisher very quickly. And then I'm going to talk about nonlinear sigma model, which is a very beautiful trick. So the idea is that lower dimensional QFTs are okay and they're nice and we have examples of them. So we're going to explore, build a whole bunch of models of it. Good? Questions? So what was Wilson-Fisher? Wilson-Fisher and D equal 4 minus epsilon. Your beta function is minus epsilon lambda plus n plus 8 lambda squared over 8 pi. So here you might actually worry, based on what I just told you, there is a linear term, but that's an interesting thing for you to think about. That can only happen because of dim reg. So the Wilson-Fisher says that in 4 minus epsilon dimension, there is a cancellation of these two terms within perturbation theory. That declares that this value of the coupling, and you end up with a new fixed point. So you can integrate the whole theory from the UV trivial fixed point to some interacting fixed point, and you can calculate the anomalous dimensions, all the operators over there. Now, this is kind of weird because it's 4 minus epsilon dimensions, but the ON model gives you better context for this. So if you repeat the calculation of the ON model, what you find is that, this is n plus 8. So you find that the coupling is like this. So now epsilon could be analytically continued to 1. So this is in 3 dimensions. If n is large enough, you remain within perturbation theory. Right? So these are rigorous. The ON, the symmetry group, allows you to define these theories that are interacting. These are called Wilson-Fisher fixed points. So these are genuinely interacting fixed points in D equals 3 at large n that are reachable within perturbation theory, and we discussed examples of this last time. Like the relevance of these models for physics. All right, questions? We have a lot to cover today. So more examples of interacting field theories is what we want to do. We haven't found so far any interacting theories in 4 dimensions and above, but we seem to have a zoo of lower dimensional quantum field theories, in particular in D equal 2. Why do I say that? Why do I say in particular in D equal
2? CFTs. I mean, the conformal group is biggest.
It's just a simple argument I've said many times. Scalar field, what's this dimension? E minus 2 over 2. What does this mean? It means that your arbitrary interaction potential is classically marginal. Right? So then it's like you have a good chance of building all sorts of interacting theories. And indeed, there's a zoo of these theories. There's the 2D CFTs we were discussing last time, but in 2D, there's a beautiful. The dimension is low enough that things are good. How about 1 dimensions, by the way? How about 1 dimensions? So today we're going to talk about
It's quantum mechanics.
Yeah, that's quantum mechanics. It's even nicer in a sense, but it has some issues. We have actually talked about this in previous QFT1 in detail. In lecture 2, we talked about that. But anyway, what is QFT in 0 plus 1 dimension? It's quantum mechanics. But it involves a trick. The trick is that your phi, so your phi is a function of t. Now your phi is xi. Your phi is an operator. Time is just an external parameter. Now your phi is like x, so it's an operator. It becomes quantum mechanics. But what you do is that you change the interpretation that you used to have. You used to think of the fields as functions living on space-time. Now time is still the same thing, but space becomes a field space. You interpret the field space as space. This is the main idea that underlies a nonlinear signal model. Well, we're going to get there. And string theory and all of those examples, those theories. All right, good. So what are we going to do today? I'm going to go in detail, and I'm going to do this in a little bit more depth. I'm going to do 0 plus 1 dimensional QFT and interpret this. This is very, very, very simple theory. I'm going to show you that this is quantum mechanics of a relativistic particle. Well, actually, you could pick a theory that corresponds to a relativistic particle or a non-relativistic particle. We only really talked about the non-relativistic particle. I'm going to talk about relativistic particle. And what is really amazing that comes out of this is that this is a theory of quantum gravity. We'll see that. And then once we're done with that, there's no gravity in the picture, but there's a sense in which it's a theory of quantum gravity, which is the starting point of string theory. But then once we do that, then we talk about quantum field theory in 1 plus 1 dimensions and nonlinear signal models. So the nonlinear signal model, this is precisely what a nonlinear signal model is as well. The simplest example of it. But it's like a warm-up calculation. All right. So non-relativistic free particles, 0 plus 1 dimensional QFT. What do you have? You have space-time is just time. And at each moment in time, you have this auxiliary space. This is the field space, right? So your field is phi, but it's actually xi of t, right? It's like I don't know if you guys are familiar with, it's like a fiber bundle. At each point sits some manifold. But that manifold, this is like internal degrees of freedom in a sense. We're going to interpret that as space. And that's how the connection to quantum mechanics comes about. As I said, in quantum mechanics, x hat of I is an operator. In QFT, space-time coordinates are coordinates. They're not operators. T, in this example, remains a parameter. In quantum mechanics, T is not an operator, and that is very natural in connection with QFT. However, X is an operator because X in this analogy is nothing but the field phi. So it's an operator. Now, in this story that we said, space and time in this picture are treated differently, as is the case for a non-relativistic particle. So why is this a non-relativistic particle? Let's write down the kinetic term. This is now, and say it's like a RD minus 1 copies of scalar field, right? That's what it is. It's a vector field. Now, if this is to be interpreted as space-time, what are the symmetries that you have? These are, when you interpret your internal manifold as space, sorry, no, I shouldn't say time. Your internal symmetries and space symmetries are swapped. What you used to call internal symmetries now have the interpretation of space symmetries. So if you would like this to describe in quantum mechanics a non-relativistic particle that actually moves in space, in your space you have these symmetries, RD minus 1, those are translations, and then rotations. So these should be the internal symmetries of this theory. So let's write down an action for such a theory. So the del T phi squared, so this is just, this is field theory action. This term is okay. It's there. I can't have a mass term. It's forbidden by translation symmetry. Right? I can't have a mass term. This is also SOD minus 1 symmetry that makes me put the indices like this. Rotation symmetry in space. Good? That's a non-relativistic free particle. All right. Now, but it's pretty clear that here space and time are treated separate, very different, right? Time is always an external parameter. Space is not, because space is the field. Now, if you want to get the relativistic particle out of this picture, you're going to run into some trouble. It's pretty clear, right? What's going to happen? Do you have a guess how it's going to work?
Proper time. The new parameter becomes proper time, and then.
Yeah, but It's a little bit more involved, but okay. All right, I'm gonna. A lot happens here. There's a lot to unpack here. So, what is a relativistic free particle? We're gonna do same thing. We're gonna have a function zero. This is 0 plus 1 dimensional QFT. Now, I'm not gonna take only xi as a field. X0 will be a field as well. X0 will be a field, but there is a distinction between time here and the time on the field manifold. Because on the time on the field manifold is just a field component. It's one of the components of the field, right? So this is an external parameter, but there is x0 as an operator. Good. Now, in comparison with what we just did, it seems like I have some redundancies, right? In the previous example, when I got a non-relativistic particle out of this, I only had xi's. I only, like say if I'm in 3 plus 1 dimensions, I only had 3 fields. Here, I want to describe a 3 plus 1 dimensional relativistic particle. I introduced 4 fields. There must be a constraint. And that constraint should somehow impose the relativistic symmetry. But what is that constraint? That symmetry is it's an internal symmetry, right? It's an internal symmetry because it's all in the field space. So let's use a language. Let's just set the language just so that I don't have to say field space all the time. So the field theory we said in Q1 is a map from space-time manifold M, this is a Lorentzian manifold, right, to some manifold X. This is where the field takes its values, right? This is the field thing. So space-time transformations or motion over here, and these were just like, say, SUN, SON, ON, all the symmetry that we're talking about, right? Let's give these names. We're going to call this the target space. And then this is the, yeah, let's call this the target space. I've been calling it the field space, but let's call that target space. Okay, so when I'm talking about this 0 plus 1 dimensions, it's this guy, that's 0 plus 1 dimensions.
In the case of QED, what is the target space for the spin?
So pick, yeah, so anyone wants to answer that?
What's the target space for the spin? For the spin? C4?
C2.
C4.
Any other guesses? How many components does that? What fermion do you want to pick? Pick one. Dirac fermion.
C4.
How many dimensions are you in?
4 space and dimensions.
Space time. So that's your. So first of all, so you have psi. How many indices it has? There's alpha here. So that runs from 1 to 4, right? And it's a map from R3, 1 to what? Each psi alpha takes values in C, complex numbers. Okay. So you got your answer. Indeed, C4. Okay, good. Now, all right, is it clear that we have some redundancy? I have a field x0 that's supposed to be time in target space. It's an operator. And then this is the physical time here. This is an external parameter. All right, so this is what we want to do. Now, let's forget about the fact that it's a QFT. Let's talk about what is the action here we're going to write down. This is supposed to be, in the target space, it's supposed to be a relativistic free particle. What's the action for a relativistic free particle? Hopefully you remember from your relativity that is minus m integral of the proper time. That's just proper time. From some t tau I to tau f. That's what it is. Okay. In the language of this map, what is it? It's minus m integral. So S is this parameterization. There's a map that sends this so that there's a world line. The world line is where how our t is embedded inside the target space. That's the world line of a particle, right? So this is the embedding. And the action is minus m integral square root of del x mu del s del x nu del s integral d over s of this. This is what the proper time differential is. Good. Why is it this? Well, it's manifestly SOD minus 1 comma 1 symmetric. That's Lorentz symmetry. It's also manifestly translation in space-time symmetry. But these are all target space, right? And then the most important part, well, take this equation, this action, vary it with respect to L del x mu. That's your field. This is your variation. What is the equation of motion you find? You find this is the variation, it has to be equal to 0. That tells you that the variation of P mu should be 0. That's what a free particle is. That's what deserves to be called a free particle. Good? All right, is this part clear? Can you see what the trouble is? There is a problem, and there is a weird feature, and they're related. I don't expect you to see the weird feature yet, but the trouble. What is that? Do you see the trouble? Look at that action. What was the action that was describing a non-relativistic particle? The action was integral of del xi. Let me write it this way so that it's pretty clear. Squared. Sorry, xi. No, xi. ls, right? Minus I. How are these two things different? First of all, what does this look like? This is the field. So this looks like del t of phi I squared. That's a familiar action. Is that a familiar action? No. That looks like, from the point of view of the field theory, it's an awfully interacting theory. Just, it's a crazy thing, right? That's problem number one. It doesn't look like it has standard kinetic terms. It's supposed to be a free particle, but it looks kind of crazy. What other thing can you see? Can you notice over there? This is, I don't expect you to see. Is the integral, so actually I do expect you to see. It's written all in terms of the proper time. This S is completely independent of S. S is a parameterization. So it's as if your action, you write down an action for your theory that's completely independent of the choice of coordinates in space-time. That's diffeomorphism invariance. All right, let's go slowly. I didn't say it's problematic, I said it's feature. The problematic thing was the fact that the kinetic term is not Gaussian. All right, so there are two notions of time here. I repeat, there's the world line time, S, and then there's a target space time, which is X naught, which is a field. One of them is an operator, the other one is a parameter. To interpret target space as space-time is better than the action is independent of the coordinate S. This is reparameterization invariance. It better be like this. So the fact that this action is independent of S is sort of needed for wanting to interpret target space as space-time. Because if you're interpreting target space as space-time, your action depending on some auxiliary, bizarre, unphysical thing is just nuts, right? You write down an action in your target space, and that's physical, and everything is local and nice. The locality, all of this is moved to target space now, right? All the symmetries, locality, all the nice principles of quantum field theory we're talking about, it's all in the target space now. For this action to be dependent on some external parameter. It's as if somebody outside the universe has a time, and your action that you write down for your universe depends on those parameters. You don't want that. So that's called reparameterization invariance, and that's desirable. That's why, well, in this action, that does have that. We're going to exploit that, but it has very dramatic consequences. Is the idea clear? It has reparameterization invariance. So how do you see it? Just send S, this little s, to T of S, right? So here's what your map is. This is your S. This is mapped to space-time, x1, x0, something like this, x mu of S, right? Now make the following reparameterization. Send S to some arbitrary function of T. It has to be causal, actually. It has to be monotonic. So that it can be order changing. It has to keep the order up. But if you do that, just see how your action changes. It doesn't change. Right? Because derivatives of S with respect to T come out, there's ds, they cancel out. So it's reparameterization invariant. Now, do you see why you need a square root? Square root is needed if you want reparameterization invariance. If you didn't have, so how is this not a big deal in quantum mechanics of a non-relativistic particle? The quantum mechanics of non-relativistic particle does have an absolute notion of time. This doesn't. This is relativistic. This is that extra constraint that I was talking about. Right? In quantum mechanics, time is absolute. There is a Hamiltonian indeed depends on some absolute time. Of course it does. Right? So two issues. One is that the action doesn't look conventional, but sort of required by this feature, which is reparameterization invariance, which is perhaps new, but it's sort of needed for interpreting the target space as space-time. Everyone is with me? I haven't lost you guys yet? All right. So to repeat, the problem is that the action is no longer Gaussian. It doesn't look like this, and it's unnatural from the world line perspective. From the point of view of, sorry, it's natural from the world line perspective, but it's unnatural from the field theory point of view. There's a trick. There's a beautiful trick. The trick is this. Introduce, so what are we trying to do? Let me write it down. What we're trying to do is we're gonna write this action minus m eta mu nu del x mu del s del x mu del s yes in terms of something that looks like standard kinetics. But we're going to pay costs. We're going to introduce a Lagrange multiplier. So how do we do this? Introduce some auxiliary new field that's non-dynamical. We're going to see what it means. And that is, so that's E of S. It depends on S. Turns out you could write down the action that you wrote, this action, in the following form. I'm going to prove that to you guys in a bit. But let's first stare at this action. It has the nice kinetic term for x mu, as expected. And E of S doesn't have the derivatives of E of S don't enter. So it looks like a constraint. Is that clear what is meant, what I'm just saying? If you path integrate over something like E of S, all it does is that it will apply constraint. Right? It's like a Lagrange multiplier. That's what it is. It's literally a Lagrange multiplier. So, all right, how do I see that? Well, let's write down the equations of motion for the field E. Of course, it's non-dynamical. So what's going to be is that del S del E equals 0 will fix for you what E is in terms of the field X. It has no dynamics. It has no derivatives. It's fixed. This is the value of ES it can take. You can solve for this and plug it back in there. All right, let's do that. You solve for this. E becomes 1 over mx dot. Good. Let's plug it back in there. If you, this is your action. Let's define x, this guy. Let's define this guy as x dot squared, shorthand notation. If you plug in this inside the action, what you're going to find is that it's an integral of x dot d of s, which is the relativistic answer. Indeed, this not only will make the action, bring the action to the standard form, but we'll see in a second, it will ensure that reparameterization invariance is there.
But that's just an answer, right? You just.
Well, I wrote it down and I showed to you that it is equivalent to this.
Yeah.
Now I'm gonna tell you what is actually doing, and for as a physicist, that's all that matters. Remember, the fields are dummy variables inside the path integral. These are variables I'm picking. I could do whatever I want as long as the variation of it on the if it's non-dynamical, it's just a Lagrange multiplier. Who cares, right? Now there's an important lesson to be extracted as how introducing E restores your parameterization invariance. Can anyone see that actually by staring at? So this is the action you want to take seriously now. Can you see what E is doing for you? I want you to be able to guess at this. Yeah. Any guesses?
Does it get rid of factors when you do like a coordinate transformation?
Of course it does. But does it look like something you've seen before? What is the action of scalar field in flat space? The action of scalar field in flat space is minus half del mu of phi. Oh, yeah. Okay, let me write it this way. Eta mu nu del mu of phi. What if I have curvature? I have some curved metric. What is the expression for it?
G.
Well, do it right. Tell me.
G mu.
Okay.
Del mu.
Okay.
Phi. And there is a term. The
Square root minus g. Good. All right. Does that look like this? What space-time dimension are you in? You're in 0 plus 1 dimensions. So your g is just GSS is just a constant. Now, let's say your GSS is eta. Make a change of variables, right? How does a metric transform? Let's go there. So send S to S prime of S. And set del S prime del S as E of S. Under this diffeomorphism, reparameterization, your metric changes by 1 over E squared. Your square root of eta goes to square root of eta E. So this expression is nothing but this expression. So now can you answer how did introducing E of S made the theory of parameterization invariant?
It's just curved space somewhere. I mean, that formula
That's
is
a curved space time, but it's not still reparameterization invariant. We did something extra. It's not that I just added this new field. To show that this action is equivalent to previous action, I had to do something else. What was it? Path integral over yes. In Lagrange multiplier, you add a term and then you integrate over things, right? So when I do path integrate over E of S, what am I path integrating over? All metrics. You are building if you're quantum gravity. You're path integrating over the metrics, and of course it's going to be reparameterization invariant. Right? You're integrating over the metrics. Good. So in the quantum theory, what you're doing is that you're path integrating over all these metrics. These are explicitly you're path integrating over all these reparameterizations, the effective reparameterizations. And in effect, it's a Lagrange multiplier. And yeah, it's basically what it does is that it gives you back the old relativistic theory that you know. All right, good. what is this constraint? This was a very weird roundabout way of imposing the constraint, right? What is the physics of this constraint? Can you see there's something funny about this action. It's Lagrange multiplier method. There's something funny about it. Well, it's not funny. It's something that like, not haha funny, but like not familiar perhaps. All right, here's the action. Let's compute the Hamiltonian for the x mu. Let's calculate the canonical, the conjugate momentum. What is that? Del Lagrangian density respect to del x mu del s. This is what the Hamiltonian is. You have d of m, right? The space-time number of these. Let's calculate the Hamiltonian density. It's pi mu del mu x mu del s minus Lagrangian density. I've done the calculation for you. Once you plug in the value of E is 0. Your Hamiltonian is 0. Why is that? Why is your Hamiltonian 0? First of all, every time every parameterization invariance, your Hamiltonian is going to be 0. That's the so-called Hamiltonian constraint. H is equal to 0. Why? It makes perfect sense. Because you're writing it from the point of view of the field theory, you're writing down a Hamiltonian that doesn't depend on time. It's reparameterization invariant. So what is that going to be? There's Hamiltonian is 0. The only way for it is that Hamiltonian is 0. Right? It's complete. There is absolutely no notion of the parameter of time that we introduced as an auxiliary parameter. There's absolutely no dynamics associated with that, and that means that the Hamiltonian is 0. As an operator is 0. This is a feature of any theory of quantum gravity. If you just did quantum gravity in the canonical sense of it, this is called the Wheeler-DeWitt equation, the Hamiltonian constraint of the Wheeler-DeWitt equation. But this is a very simpler case. You don't need to do any of those fancy things. This is just, there's no gravity in here. The gravity in this comes from the fact that this Lagrange multiplier could be interpreted as a path integral over the metrics. The metrics are stupidly simple, right? It's just a function worth of path integral. Good. All right, this is all I wanted to say about nonlinear sigma model in 0 + 1 dimensions. Question, yeah.
So can you repeat what you said about the Hamiltonian constraint? Because
just calculate the Hamiltonian.
Yeah.
Just calculate. And once you plug in the condition that E is x dot over m, the equation on the equation motion is 0.
But why is the way of reparameterization really required then?
Because this Hamiltonian tells you about, this is from the point of view of the 0 + 1 dimensional field theory, right? From the point of view of the 0 + 1 dimensional field theory, your variables are x mu's are functions of s, but your action doesn't depend on s. So Hamiltonian must be 0. There is no dynamics. You introduce an external parameter, an external clock, and then you require that nothing depends on it. So the thing that generates Hamiltonian corresponding to that is going to be 0. That's the only way for it to remain consistent. All right. Next. Oh, sorry. I think I'm missing a slide here. Yeah, let me tell you, or draw the slide. So what is nonlinear sigma model? Nonlinear sigma model is a model where you exactly do this. You have a field theory like this, and this is the target space. This target space, well, actually, sorry, I should say nonlinear sigma model. You take this target space and you take it to be a nice manifold. It has a lot of symmetries, and you use those symmetries to make sense of a nice theory. So we're going to talk about, so for example, the example of nonlinear sigma model that we just saw was the case that this was R3, 1, right? This is 0 + 1 dimensional. Now, why is this helpful? Because we saw the quantum field theory, whether it's well behaved, whether it exists or not, is only sensitive to the dimensionality of this M. As a matter of fact, if this target space was bigger, it was helpful for making the theory well defined, as we saw in the ON model, right? Large N made the theory better, right? So one nice perspective is, well, okay, I just did for you 0 plus 1 dimensional M. You could try to have this take the point of view of 1 plus 1 dimensional to X. This being target space being your space time. That has a name, it's called string theory. That's the origin of string theory. But we don't want to teach string theory here. What we're going to do next is we're going to discuss examples of nonlinear sigma models in 2 dimensions. This is 2-dimensional, right? 1 plus 1 dimension, and X. What I mean by nonlinear sigma model is that X is a group manifold. We're going to see that. We're going to see that, okay? But there's a target space here, that's nice. In particular, what is the action I'm going to write? The action. So previously, when we wrote, if you have a bunch of, so think about this. Think about this action. Phi I nu eta mu, right? This is an action. This is the space-time metric, but I've used the field metric. There's an internal manifold here. There's an ON symmetry. And that field metric I've used is just 1, 1, 1, 1. Right? You could, in nonlinear sigma model, you could introduce a non-trivial field metric, Gij here. Now it can depend on the field phi. This is the metric on the target space. In this picture, I was just advocating viewing target space as space-time. This would be actually metric over there, right? But every time we write down an action, so far I've been saying ON symmetry. I've been saying like a UN symmetry. That means that I'm picking X and the metric on X to be a very, first of all, very symmetric space and a very canonical metric on it. That was what's been helping me simplify the model. Now, nonlinear sigma models are when you start with a theory that looks free. The kinetic term of it has flat space-time metric. You make interactions by putting a metric on the field space. This is what nonlinear sigma model is. Now, do you see why the example I just gave you, the relativity free particle, was nonlinear sigma model? Because I had a metric, right? The metric was E of S in a sense. And over there, I actually path integrated over the metric. Here, I'm not going to do that. So this is not going to be a theory of quantum gravity, but I'm going to pick a particular metric and put it in here. That's like fixing a value of E of S, right? Okay. Is that notion clear? The simplest example of nonlinear sigma model we're going to discuss is an SON symmetry case. Now, why is this theory nice? Because we're going to stick to 2 space-time dimensions, but we have this freedom to play with the metrics here. And we might end up, as we'll see, we do end up with a large class of sensible theories. The fact that they're going to end up being sensible is sort of guaranteed. Well, it's helpful that you're in 2 dimensions. Now, these are going to be the very first examples of theories where not only I say, so far we've been saying that whether the theory exists or not is about whether the beta function is like negative. That's all I meant. But beta function being negative, it doesn't mean that you have full control over where the theory flows, right? So if you're within perturbation theory, Wilson-Fisher was nice, we found an fixed point, but we don't really know what's going on. Like if you took the second theory and this like perturbed or something, right? It's complicated. Here, what we're gonna do is we're gonna see this symmetry. We're gonna pick a large symmetry group, and it will tell us about the type of terms that are allowed to be generated through the RG flow. They're constrained. All right, is the idea clear? The simplest example of a nonlinear sigma model is I'm going to pick R2 and I'm going to pick the field to be a vector on a sphere. Sn minus 1. My field is Sn minus. So if my field is some vector ni, it means the sum of I and I squared is equal to 1. Is it clear why this is called nonlinear sigma model as opposed to linear sigma model? If it's not clear, let's do it. So this is an ON model. This is a linear sigma model. The nonlinear sigma model has this extra constraint that n norm of it is fixed. That adds nonlinearities. How? So one way of seeing, as we just saw, Lagrange multipliers, is that you path integrals over all in I, but you have to put inside your path integral explicitly this delta of n squared equal 1. This you could write down as by introducing some auxiliary field, lambda of x, and then this is the term that it adds to the Lagrange, and this is Lagrange multiplier methods. Do you see that is nonlinear yet? Okay, you don't see it yet. Next slide, you'll see it. Is everyone with me? Is it clear what I'm doing? So I'm just doing ON model, linear sigma model, with an extra constraint that sum of fields, they add up to 1. So the field lives on a sphere. The field is not allowed to fluctuate in its absolute value. All right, so let's solve the constraint and see its nonlinear sigma model. Pick ni's to be pi 1 to pi n minus 1 and sigma. A way to impose a constraint is to say sigma is not a brand new field by square root of 1 minus pi squared. All right, so now this is your initial Lagrangian could be written this way. Why? Let me do this for you on the board. So what is it? It's del mu and I, del mu and I, right? And then I have the first n minus 1 components. They're going to look like x mu pi I, x mu pi I. So this is a linear sigma model for ON minus 1. Now, the nonlinear term, I should write down del mu of sigma, del mu of sigma. But what is sigma? Sigma is square root of 1 minus pi squared. Take derivatives, plug it in there to find that action. So is it clear that's nonlinear now? It's pretty clear it's nonlinear, right? But the nonlinearity is a very, very particular form. You could interpret that term in 2 ways. First of all, you could interpret it as a metric on Sn minus 1. What is the metric? It's just this, right? It's just this expression. This expression is nothing but pi I, pi j contracted with this metric that depends on the field. It's a metric on a sphere. That's what it is. It's round sphere, round metric. So that's why it's a nonlinear sigma model. Now, these, from the point of view of the n minus 1 field pi's, have the interpretation of interactions, right? They're interaction terms. There is actually an infinite number of them. Do you see why? There's 1 minus pi squared in the denominator. If you expand that, that goes all the way to infinite orders. Yeah.
No, sorry.
So there's, but this, so this isn't, so you know when I wrote lambda phi 4, when I took del mu, when I took this theory in Q of T1 and added lambda phi 4, you know, we saw that when you do RG, all sorts of higher order terms appear, right? So there was nothing special about this term. Right? Anything could go. But now I have some sort of grand principle that suggests an interaction term that, first of all, is to all orders. It has a very specific form. like that. And we'll see that under RG, that symmetry protects it. It will actually, not all terms are allowed, because RG can generate anything that doesn't violate symmetries. But anything that violates this the SON symmetry cannot be generated under the RG. So this is an exact action you can write down, right, to all orders in perturbation theory, and you're guaranteed in it. Well, we'll have to see actually how it works, but at least at this level of arguments, it seems very natural that under RG, nothing crazy will happen to it. The structure will be formed, right? All right, questions? So that's the point of nonlinear sigma model. In sigma model, when I added lambda phi squared, lambda, like the mu phi 4, whatever I added, I was just randomly writing whatever I could write with ON. I didn't have a hard dimensional symmetry principle. Here, there is a hard dimensional symmetry principle, SON, that tells you that from the perspective of n-1 fields, this interactions are very, very fixed. So now, up until now, you might have been one of the things that you haven't probably, you might not have been very familiar with, is that when I wrote, like we said, I write down Lagrangian Landau's principle. I just write down in derivative expansion whatever I can write down that's consistent with symmetries, and then I'm going to pass integrate over them, right? But now you know that because of Lagrange multiplier methods, if you have a constraint, like you want to say that you write down the most general action, but then you want to rule out some of those terms, you say you invent a symmetry that forbids them, right? And you put that symmetry as, you could put that symmetry, you could do your standard path integral and stick it as a Dirac delta function, functional value thing inside the path integral, or you could exponentiate it as write it as a non-dynamical Lagrange multiplier field, some auxiliary field. Both of them go, right? This is actually the case in gauge theories. Good. ON symmetry, so this is the right terminology. ON symmetry is non-linearly realized. ON-1 symmetry is linearly realized in this writing of the action. The quantum theory, from the perspective of quantum theory, there's nothing fundamental about the field pi, vector pi. That's one way of organizing your degrees of freedom. You're going to path integrate over it anyway, right? It's just a basis. It's a frame to describe this theory. This frame, in this frame, the SON symmetry is nonlinear. Sorry, SON symmetry is nonlinearly realized, and ON-1 is linearly realized. Good. This, I said before that this includes an infinite number of interactions dictated by the symmetry. But the most beautiful thing about it is that when we had the running of couplings, all the couplings could run. It was an infinite dimensional space. Here, there's only one coupling for all of these guys. There's only one coupling, right? They can't be, if you, again, RG has to respect the symmetries, right? It can't, these guys are locked together in that non-perturbative expression form of interaction. So this is a method for generating truly interacting theories that you have some nice control over, nonlinear sigma models. All right, so I'm going to do a calculation. I think I have time to do this. Start the calculation, but I'm going to pause for a question. Is the principle clear? A field theorist has a bunch of key tools in their toolbox. Like symmetry, larger dimensional symmetry that's realized non-linearly in terms of some lower dimensional degrees of freedom is one of them to write down interacting theories. And we write them down in 2D. 2D nonlinear sigma model is particularly nice because the 2D-ness of it makes, so the coupling of this term, what's the dimensionality of it? is dimensionless. Right? These things matter. As we go to higher dimension, I'm going to give examples of a higher dimensional nonlinear sigma model in the next lecture. We're going to see it's a little bit more restrictive, but 2D is pretty nice. 0 plus 1 is even nicer, but it's kind of stupid. It's just world line theory. All right. So now this is our action. What we're going to do is we're going to write down Callan-Simanzik for correlators of pi and phi and sigma. Right? We'll compute them. Compute beta of G. There's only one coupling again. Remember, there's only one coupling. We're going to find it to be minus G cubed over 4 pi and minus 2, which is good. Why? Because for n larger than 2, it's negative. So this naive dimension counting marginal coupling is actually relevant. Okay, so start with the 1-point function of sigma. This is what we're going to calculate. By ON minus 1 symmetry that's preserved, we know that pi i's of 0 should be 0. Right? There should be no 1-point function for pi I. So sigma of 0 is expectation value. What was it? It was what is sigma? Sigma is square root of 1 minus pi squared. So just expand it and expand the derivative. Sorry, square root. Expand the square root. And you're going to end up with an expression like this. I think I'm missing a half. Am I missing a half? Yeah, I'm missing a half. Yeah, I think. I thought I had a different normalization. This is odd. Okay, anyway. So this should be 4 actually. So what is this? Oops. What is this diagram? This is just from the point of now we're going to do this calculation from the point of view of the interacting field theory of pi's. So this is this Feynman diagram at 1 loop. All right. Let's calculate it. What's the propagator for pi I pi j? It's just ig2 over p squared delta ij. There's no master. So this becomes ig2 n minus 1. Why n minus 1? There are n minus 1 pi fields running in the loop. Integral of d2 of k 2 pi 2 1 over k2. This is both uv and r divergent. That's pretty darn bad. But let's not worry much about it and do Wilsonian RG. So let's say we have some m and change it to b. So let's do an infinitesimal integration in momentum, shift in momentum. And then we find that whatever the 1-point function of sigma is at scale m, at some lower scale, it will run by this much. All right. This is enough for me to write down to the lowest order Callan-Simanzik for this 1-point function. So mddm of gamma of g is this. I can take mddm because it's bdb of this, and I find gammas are g squared over 4 pi n minus 1. So what remains to be done, do you guys have 5 minutes patience? She's gonna finish the calculation, okay. What remains to be done is, well, I calculated this gamma very efficiently, very, very quickly. Next, I'm gonna calculate for you guys beta. There are things about this beta that you should be a little bit surprised by. By the way, look at this. Why is it G cubed? Does it look like something you've seen before? QED. Yeah, because you're writing in the coupling, the true coupling is actually G squared. Do you know why? When you in QED, when you do these kind of scatterings of fermions, how many what's the coupling? It's always E squared, right? Similarly here, from the point of view of pi fields, if there are a bunch of pi fields that come in, the coupling that will be relevant is g squared. Now, if you rewrite this in terms of g squared, it would be minus g squared. So the coupling is g squared. All right. So next, what we're gonna do is calculate the look at the Callan semantic for the 2-point function as one loop of pi and use it to calculate the beta functions at lowest order. So what's the 2-point function? The 2-point function is ig squared, or well, you already see g squared here anyway. Ig squared over p squared delta kl. That's a true level. And then there's an interaction term, and hopefully you remember what this pi kl is. So these guys are these two legs. This pi kl is. So it's a vacuum polarization indeed. You write down the Feynman diagram for the 4-point function from the expansion of that nonlinear action. This is what the Feynman diagram is. You just need to close one loop, and this is what you get. That's a couple of lines of algebra. Now, this diverges as lambda squared, and that is bad. It's not consistent with the ON symmetry. This is reminiscent of another thing we've seen before. This happened in QED as well. There's a lambda squared divergence that violates the symmetry we have. Over there, it was what was being violated. There was a lambda squared divergent term. You need logs of lambda. Over there, what was violated was ordered identities, the gauge invariance, right? Similarly here. So what took care of that? Do you remember what took care of that divergence? Yeah, but when we did that, there was a counter term. There was a counter term that canceled that. Here, there's a counter term. What is that counter term? All right, let's derive the counter term and I'll be done. Here's that path integral, right? Integral of d of ni, pi ni, e to power s ni, and this is the condition. We have constraint. Write this condition explicitly. Sigma of delta of sigma squared plus pi squared minus 1. Now, this is second order. If you have this, do you know how this delta of x squared is related to delta of x? There's the derivatives that come in. Here's what that derivative is. Now, this you deal with the standard way you deal with, but this square, this guy in the denominator, exponentiated, becomes e to minus sum over x ln of 1 square root of 1 minus pi squared. In the action, the coefficient for this is delta squared of 0. It's this divergence. This is a counter term.
How did you?
There is this condition. This condition is second order. So you write it as a first order condition and you get this derivative. This is part of the action. You have to write it, you have to take the log of it and put it up there. It will contribute to Feynman diagrams. It turns out this coefficient is divergent, which is easy to see. Hopefully you guys can see it. This coefficient is divergent. There's delta squared of 0. But what is interesting is that, can you draw the counter term? Can anyone draw this counter term? What does it look like? What's the Feynman diagram for this counter term? It's a whole bunch of counter terms. So the counter term is delta squared of 0. What is it? Integral of d2 of x ln of 1 minus pi squared. Is that right?
Yeah.
Okay. This is nonlinear. You're doing one loop perturbation theory. So linearize it. What does it look like? Pi squared. This is your counter. What? How do you draw this? Right? This is what it is. So now once you add that counter term, it turns out it amounts to, I'm sorry, I'm really late. That's also wrong. No, that's correct. Lambda squared over 4 pi, it cancels the divergence of that. You get now with the log divergence term. This is their 2-point function up to 1 loop correction. You calculate the Kalin-Simanzik, you find the beta function is minus g cubed, and minus 2 over 4 pi is asymptotically free for n larger than 2. So in summary, what did we do today? We introduced nonlinear sigma model. Nonlinear sigma model is when you have a large symmetry group, and you use that to that nonlinear that symmetry group is realized nonlinearly in terms of some lower dimensional degrees of freedom. It amounts to writing a free action for your particles in space-time with some metric, some curved metric on the field manifold. And then in the case of 0 plus 1 dimensions, we saw that this curved metric in the this theory in 0 plus 1 dimension is just really nothing but relativistic free particle. It's quantum mechanics of a relativistic particle, and it's actually a theory of quantum gravity because it's path integrated with the metrics. That's it. Thank you. So in the next lecture, we're gonna